recording is on. So, my plan for today is an application of discrete time Fourier transform. What is discrete time Fourier transform and why should we apply it? DFT, discrete time Fourier transform. It's a very useful thing. Let's say we have some signal. Periodic signal, and we would like to perform a Fourier transform on it. But we don't want to fight this mass with all these integrals. The basic idea of Fourier transform, what we can represent our signal as a DC component and a sum of ideal cosine and sine ideal harmonic components. We can represent any periodic voltage or current or anything with the sum of one, let's say, DC component and multiple AC components described by the coefficient C and S, cosine and sine coefficients. In the basics of electromagnetic theory, each, let's say, will be minus k at a frequency omega. Looks nice, but we need C and S. We need sine and cosine coefficients. Basic theory says what cosine coefficient can be defined as a double divided by period, integrating from 0 to period my signal cosine in time. The same way, sine factor is 2 divided 0 sine of above p and time. Very nice, but should I do this by hand? No. Machine works, I relax. How can I make this automated? Let's start from beginning. I need C1. Cosine for base frequency, for first harmonics. I need to calculate from 0 to 1 my signal cosine. This will be time. I'll draw something. What? Let's say I have a table of signal values. I have something like this. Time in time unit, signal at time. And number 1, 2, 3, 4. 1 unit, 2 units, 3 units, 4 units. Something here. I don't know, maybe something like this for signal. I have signal values from the first one to the, let's say, n capital 1. So, this one is the first, second, third. At the end, at the period, I have number n. This step, table step, will be period divided by number of measurements. I will use a tau letter to mark it. So, this table represents signal as a set of measurement points, yeah? Or samples. And it's a signal in discrete time, I tau, where I is a position, in fact, table number. Tau is a time step. White line is continuous signal in our space, in human. And red dots represent signal in a discrete time. Why? Computers, all digital systems work in discrete time. They always have a time quantum. Right. It's already one of these, Randy. They, for example, have a time quantum of 1 millisecond. Voltage and current are stored in memory with a step 1 millisecond. For this unit, time step is 1 millisecond. All digital systems work in digital time, in discrete, in interrupted time. Our time is uninterrupted. But for digital system, time goes in steps. Okay, I have signal representation in computer memory as a table of discrete values. Now, let's go forward.
Professor, that C1 is it for discrete time or is that?
It's a number of measurement. It's just a number of measurement.
C1.
C1. This one is for analog, for uninterrupted time. This one.
For continuous, right?
Yeah, this one is continuous. Now we see it's in discrete.
Yes.
One moment. See what we need? We need to integrate. I don't know. Let's say, for example, this is signal multiplied by cosine. 1 is equal time. It's a multiplication of sec multiplied by cosine. I don't know how I look for example. It's not important.
Okay.
What's important? What the physical of what the, let's say physical meaning of this part? Area of this figure. I don't know the signal. I have only table. Anyway, I can draw these nice points because they are measurement. So this one will be for I1, 2, and so on till number of measurements. White line is continuous signal multiplied by cosine. Red dots, my signal of I tau multiplied by cosine. Since I knew values of the signal only at measurement points, it is not important actually what between them, I don't know. But what I'm trying to do, I need area of the white figure. But I have measurements only at red dots. I'll connect them like this. What I'm getting? Set of rectangles, such pillars. I can say what white area is approximately equal to the red. Approximately. What will be area of one such object?
Length into breadth.
It's a rectangle, so length multiplied by width. What is length of the height? What's here? It's a signal value at a point of I tau. Yes? Multiplied by cosine of what? What's the angle at this point? Period equals for cosine to double p radians. When t small time equals to period, this one is unity and remains only 2p radians. I have n capital measurements. So one step, and for cosine, one step will be, is it correct? Yes. Divided by number of measurements. For this one, cosine, it should be I multiplied by. Yes? But there is one moment. Many literature sources ignore it. See what the point is. I start number points from the one. First one, second, third, and so on. But what the value of angle at this point? Zero. If I started numbering from 1, I need to correct it. So height.
That's if you start from 0.
Yeah. Or I should start from 0. This means what this point is not the n but n minus 1. Anyway, this shift on the 1 is unavoidable.
So those are the values, right? The values at the point.
Yeah, signal value at the point multiplied by cosine. The on moment I need to take into account shift by 1. Because cosine angle starts from 0. At the first measurement, cosine should have 0 value argument. It's okay with Okay, but now I need width. And width will be period divided by number of measurements.
So why don't we just start from 0 then? It's easier than avoid the -1.
No.
We need to do something.
No, many digital systems require that array's first element be number 1, not 0. Anyway, we introduce this shift. We will introduce it with numbering.
Okay, so Professor, we do all of this just to find the first harmonic?
We will globalize it to find all harmonics. You see, the idea is very simple when you see what's behind. Usually in literature you will see ready form, just sum. Now, one moment I'll show the easy result. What's the easy result? I need to count them all together.
This is like trapezium rule, right, Professor?
Yeah, it's rectangular. I can switch to trapezium.
Yeah, it's like that. Okay. Remember learning it.
I can, let's say, point. I can connect like this, and it will be -1 cosine of I minus 2, and so on. Half of the sum, but result.
It approximates it.
Yes, results appears approximately the same because difference in overall formulas will be odd at the ends, where usually we have 0 near 0. Only if we take periods at a 0 crossing, difference between rectangles and trapezium formulas will be only at the beginning and the end. But since we begin at the end at near 0, they are not playing math. This way is okay. What should I do? Yeah, I should write now C1. How can I? It will be multiplied by, divided by number of measurements and sum of all rectangles. I from 1 as I down cosine I 1 here it is. I can.
Professor, why is there an I, SI tau? Isn't it just S tau?
No, because tau is a time step.
Yes.
And I is a number. The first measurement will be
1, 2, 3,
yeah. We can use. You can. If you have an array of measurements, it will be just element of array.
Just key or something.
So time, we can forget about it. Nice. Now we need to extend this formula to any harmonic. This one is for the first one.
Professor, isn't that 2 pi over n or 2 pi over n? In the end, 2 pi over
Yeah, it should be n. Sorry. Yeah, it should be number of. It should be number of measurements. Now we need to extend it, and this extension is very easy. If the first harmonic at, let's say, 50 Hz made one turn during the 20 milliseconds. Second harmonics, how many turns will make? 2. And see not 2p radians, but 4 is 2 turns. Third, we'll make 3 turns. And instead of 2p, we will see 6p. And so on. So for any harmonic, we will see 2 divided by n multiplied by sum. What I'm doing, from 1 to number of measurements. Cosine divided by number of measurements. In the same way, sine component will be 1 to number of measurements who's writing number I measurement of the signal sine. Here it is. We have ways for discrete time Fourier transform. Way how to perform a Fourier transform with the help of computer.
Professor, why isn't there a tau or something next to I?
We can, if you want.
It's the time step, right? Basically.
Yeah, it's a time space. But in reality, when I started, I was a number of the element in the table.
Yes, it's 1, 2, 3, but tau is like the gap.
Tau, yeah, it's a gap. This I tau used to show discrete time character of the signal under transform.
So it's not important.
For us, it's anyway, it's a table of values.
So basically, we just substitute.
We just left the number of the. See, there is one moment. We by default consider equal step. But between elements in the table, steps are equal. In theory, we can usually all digital systems work with equal steps. But in theory, we can work with variable time step.
Yeah, like exponential or something. Yeah.
Adaptive. There is one of the way to compress the information, let's say sound compressing. Use derivative of the signal to determine time step. When it changes faster, time step shorter. Slower measurement, slower change, we can take bigger steps, so it will produce less data. Not in our business. Now, how to use it? Nice formulas. Yeah?
Professor, what software do you use for these functions?
I will use Scylla. 1 second. But they are software independent. Any software can be used. Capable of calculating sound.
Yes, but what's the easiest?
Easiest, MATLAB Scylla.
See that.
Yeah. It's easily available at the or any student can get.
It's free?
Scylla. Yeah, it's free. For students, free.
So we need an ID or something to register?
No, nothing. Nothing is needed. For example, I want to calculate model network power from 3-phase DC source. E. E. A. And I need another one. A power B. After all, the more aesthetic. I have something like this. Three-phase source and rectifier. For example, capacitor, coil capacitor, and something more, not important. Output voltage of rectifier. 1, 2, 3, 1, 2, 3. Something like this. It's not a DC.
Voltage?
Yeah, voltage looks like this. If I cut the schematics, without load, I will get something like this. Three-phase rectifier. It is not a DC voltage. It is not an AC voltage. It's something. No. No load. How can I solve such problem? I need to apply superposition theory in conjunction with Fourier transform. What will I do? I can replace rectifier with all its system with Fourier law. Instead of this rectifier, I'll consider this one is a base point. This will be base with pool 0 and source connected at a point. What I'll do? I have this A point, schematics, containers, not important, but I will DC component as C0, component 1 omega T as C1 minus S1, S. I will connect them one by one. S3 minus S3 and so on. I will connect Fourier components, ideal components, one by one to my network. Double omega, triple omega, and so on.
Why is the omega different, Professor?
Which one?
Why is it 1 omega, 2 omega?
Because I decompose them to Fourier law. 1 omega, 2 omegas, 3 omegas, 4, 5, 6, and so on.
But they are for all independent sources of
Yeah, they will all independent sources, each its own frequency.
Yes.
Members of Fourier rule are independent. That's why we needed an orthonormal system of function to make them absolutely independent. I will decompose rectifier voltage into set of ideal Fourier components. Connect them one by one to get partial regimes. I will get voltage vector, and so on. I don't know, number of nodes at a frequency. I will get at a, let's say, DC component at 1 omega, at 2 omega, and so on. Partial regimes. I will have voltages at frequency 0, DC component, base frequency, double frequency, triple frequency, and so forth. They're called partial regimes. I can get them easily because each of the components is ideal. And all my toolbox from the basics of electrotechnics are applicable. I have tools for DC, yeah? And for ideal AC current. And that's all. So I can use, and I will use, nodal voltages, method of nodal potential, nodal voltage, to solve my schematics at this in DC regime, single, double, triple, and so on frequency. I will get a block of partial regimes. Applying inverse Fourier transform, I will get real voltages as a time function. Decompose into ideal components, perform a calculation or solution on ideal components in the world of ideal regime, and then connect everything together with inverse Fourier transform. The same thing, branch currents. It's from Latvian, branch is thus in Latvian. Set of branch currents. Okay, I will have DC and currents. I will have branch currents at 1 omega. I will have branch currents at, I don't know, omegas. Calculating the ideal regime, this calculus yields me ideal currents. Real can be achieved via inverse Fourier transform. Okay, 1 second. I'll start my program. I'll open my program. Where it is.
For each of those elements, we need to put it into that CK and SK equation.
Yeah, we need.
Okay.
1 second. Yeah, this one is. One moment, I will capture. Hey, screen, I want to capture you. Why? Oh, yeah. And oh, yes. Can you see the text? The first part, this one. what's going on here? Table of values, maybe. 1 second. And now save as. Okay, let's take a look on this fragment. The first one, number of measurements. 708 means what I will fill half a degree.
Yeah.
With a step, half a degree. Ratio needed to convert from degrees to radians because cosine, sine and all trigonometric function require argument in radians.
That's 2 pi over n, right?
Yeah,
That's
it's
the step size, okay.
yeah, it's already step size.
Can you increase by control and scroll?
Zoom.
I'm not sure, but I can try. Maybe this way is better.
Yes.
What's the percentage for the, or what is
It's mean constant.
Ah, okay.
Percent in front of something means what it's a constant.
Is this C language?
No, it's a internal language of Scilab. Very, very simple. Now this one, I have E of 20 volts. And it's some of the task variants. But I need, for rectifier, I have 3-phase rectifier. For such rectifier, I need not the phase voltage, but linear.
Yeah.
That's why I'm multiplying by square root of 3. Now I'm filling the table of values.
Professor, so for y square root of 3? Or is that just
Because the
There's the line.
yeah, very. Wait 1 second. We have 3-phase system with equal distributed phase. So for the simples for 2p equals to 1, we will have set of coils like this in generator. If they are distributed evenly, we will have 120 degrees between the phase. For example, can be created generator with different, not even distributed. There will be no square root of 3. But since we have two vectors, let's say this one is 220, this one is also 220, and linear, if I take AB phases, what I will get? 380, or phase voltage multiplied by square root of 3, because I have 120 degrees here.
Okay, so if it's 2 phase, it will be square root of 2. It's vice versa.
With two phase, you will see like this,
Yeah.
and it will be square root of 2.
And then 20.6 is the voltage given for E.
Yeah, it's voltage given for E from the. So I need a linear voltage, and output of rectifier can be found as a. I'll switch to my board for recording. if I have rectifier powered from three-phase system, output voltage can be found, it's a little bit rough, as E multiplied by square root of 3 multiplied maximum by E of absolute values sine omega t sine omega t minus 2/3 p and sine of omega t plus 2/3 p. A There is one moment with this form. Actually, I'm introducing a shift on 30 degrees, but it's not important. It's not a crime. This one is 0. Where is my... Where is my... So, in this part, you can see I'm filling table of signal values. Biggest maximum one from absolute values of array filled with sine shift by 100 degree backward and shift by 100 degrees forward. And I want to plot it as a chart. I have ability to execute till correct. One moment. I'll bring the chart here. Chart. Yeah, that's what I got from this fragment. Looks like output from the rectifier. It is.
So this is for 2 pi, right? For one entire...
Yeah, it's one period.
One period, yeah.
One period of the network voltage.
Does it bottom out at what value?
What it should be? 20.6 multiplied by 1.7 linear voltage.
So how come it's not like this, but it's going down to 20?
No, we have three phase. If, for example, take a look. Hey, come on.
Or is it just one individual phase?
No, it's output of rectifier.
It's all 3.
All three coming together. Where is my editor? If you want, I can comment this out. It will be ordinary rectifier. Where is my mouse? Hey, mouse, come on. Yeah. This one is for ordinary rectifier, but connected to the linear voltage.
So then you get a straight line?
execute till the correct. No. This one is not so. Hey, come back. I'm sorry. Where is my correct? Come to.
Yeah, so then it will be from 0 till 20.6.
This one for ordinary rectifier. It's 4, 1, 2, 3, 4 diodes. From 0 to full voltage. But in case of free phase, we never fell to 0.
Yeah, it will always be.
It always be a DC component.
Because of the Fourier law, right? Because it is DC component plus AC component.
Not because of Fourier, because we are taking maximum, but we take in the single phase, we have sign, when we take absolute value, 1, and negative 1 will go up. So we are dropping to 0. But in case of free phase, there always will be a phase with the voltage. Okay, I'll need to. Hey, this one is not necessary. I will return to my previous. Now we can go further. We saw the port result. We saw chart. Now we need to perform a Fourier transform on it. I will, with the help of this 4, I will count it. 4 cycle, count from 1 to 3, 1, 2, 3, 4 till 50. I will use a block of 50 harmonics for AC components. You can see this part, our discrete time Fourier transform formulas. Sum C is sum for cosine, sum for sine, values of signal multiplied by sine or cosine, number from the table. See, table formed here, table of values, starting from the first one and till the number of points required. I can use more points if I need. Sum for cosine, and this sum for the DC component.
There's only one DC component.
There's only one DC component. It's always one DC component.
So
For Fourier role.
Is that line necessary then? We can just make it SI plus.
Nope. I think it's necessary.
Because it won't change, it will be the same value that we got from above, I think.
Nope. We have this one. Yeah, there is one moment. It should not be within this cycle. It should be calculated only once. It's true. Actually, it would be better to do like this. Cut this off. I did and take.
But then your C0 will be.
Wait 1 second. I need to cut it off and put it here. This one, this way is better. And final, bit more aesthetic. This way is appears what I have performed Fourier transform, but how can I check correctness of my transformation?
You can call it again.
Yeah, I can synthesize signal again and compare it with the original. That's what I'm doing. Fourier synthesis. And plot original signal. This one is synthesis. ST is synthesis. It will be drawn with plus. And original table. Let's take a look. So I need to execute till correct, and I need to bring this chart here, and it would be nice to make it
Professor, why are there gaps in the chart?
I will enlarge, you'll see it's not a one second to where is, oh, I need this one. Where is the zooming? Hey, I'm zooming you.
No, there's not a gap, okay.
Yeah, it's a bit different. There are not gaps, but you see, one is drawn with a synthesis is drawn with plus marks. See, this one is synthesis, and this one is original. There is a big difference. Synthesis, Fourier law has a limited precision. But I think it's okay. So this is my Fourier law and original interrupted signal. Anyway, Fourier law will not represent the signal ideally because it's interrupted. But
It's close.
for me it's okay.
And there was another lesson, right, Professor, on the difference between Fourier and the ideal?
Yeah, it's called Gibbs paradox.
Yes, yes.
And then I will show that this difference can be higher than 18%. But that's what we see. Appears what I have performed Fourier transform correctly. It's much. Now the next step. Now I need to calculate AC regimes. I'll start with the C regimes. Now I need to calculate 50 AC regimes. I'll use method of nodal transform. The first idea for any numerical method, I need to represent my schematic in a form, let's say, understable. It must be something what computer can understand. I need to replace my schematic with a set of matrices or functions or something like this. I'll use matrix. It's simple. Linear algebra, what we know and computers know. So the first I need to show topology, connection, branches, nodes to my machine. And I will use so-called first incidence matrix or nodal branch connection matrix. To do so, what I'm doing. So I have my rectifier replaced with a source from Fourier. It will be from, let's say, K omega. Or actually it's SK. Now I don't know. I have some internal resistance, let's say, capacitance, coil, maybe another capacitance, so on. What I need to do first, I need to assign numbers to all nodes and all branches. The only one accepting the base node. I have Earth here, it will be my base node with the voltage 0. All other, this for second and so on, and each branch will have number and direction. I need to specify numbers and direction for each branch in my schematics. When I did it, I can translate network topology into form readable, understandable by computer with the help of first incidence or nodal matrix. This one will be, what this one? Now, row number corresponds to the node number and column number to the branch. If some branch falls into node, I should write -1. If flows from, I should write 1. If has no connection, I will write 0. No connection, 0. Actually, it's the first Kirchhoff, or Kirchhoff current law. But be careful. Flows in, -1. Goes from, 1. Positive direction from bus.
So you're talking about current here? Pros in the sense current or?
There can be no current in branch. I can have hanging branch without current, but if branch exists, I can assign number. If I can assign number, I can assign direction. Okay, it's a philosophy. Electrotechnics say what they all are currents. They are numbering currents. But we can have branch without current. Okay, never mind. At the first approach, currents in forceful sense are branch. See, topology can be applied not only to electrical schematics. For example, maps, streets and roads. Also, topology, but they can be no flow.
Professor, what is this called again? The branch versus node? What is it called?
Node, it's not numbering.
Yes. It's
So,
not creating-
row numbers corresponds to number of node,
Yeah.
and column number to the number of branch.
Okay. And the flows in minus one.
Flows in, -1, flows out,
One.
1. No connection, 0.
What if it's a hanging branch? Then it's also 0, right?
Sorry?
Like a branch that you said just hanging like.
A branch was hanging? No, it has nodes. It has no, we have hanging node. Let's say network, and branch is hanging. We have a node at the end. We don't have current here, but we can measure a voltage.
Yes.
If we can measure a voltage, it's a node.
So then in that case, which?
Yeah, in the next moment we can attach something.
Just.
Just extending the matrix.
Yes, but if nothing is attached at that.
If
time-
nothing is attached, current is 0,
Yes.
but node exists,
Okay.
and voltage can be measured.
Yes.
Okay, it's maybe useless,
Useless. Yes. So what number do we?
but useless. One of the moments we can extend schematics. We can have some core schematics and then extend. In such case, core may have ports not attached at this moment, but these ports will be used in future. And matrix, attaching something, we're just expanding matrix. It's to save work. Okay, it's a philosophy. Case network for it's rectified with something. Okay, it's just a nodal matrix. The next two.
So in this example, there is 1, 2, 3, 4, 5 branches and.
No, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches.
Okay.
And 5 nodes.
5 nodes.
The next two, where's my mouse? These two are size measurements. To make what's automate, I just measure number of, first dimension is number of rows, and the second dimension number of columns. Actually, the first one will be number of nodes in schematic, and the second one number of branches.
What is that m comma 1, m comma 2?
1 means first dimension, this, to measure this way.
Okay. And second is horizontal.
Measure this way, first and second dimension. Okay, this tiny piece of code to transpose the nodal matrix. I will need transposed matrix. The same one, but let's say rotated 90 degrees. Actually, transposed means row numbers are swapped with column numbers.
What is h? That, okay.
Actually, it's a number of branches. Okay, the next one is bit tricky. This row declares omega. It's an angular frequency. Base frequency was 50. Okay, it's 2 by 50 by p by number of harmonic. This one is a complex frequency. The next one, this row, it's important. For each branch, I need to, let's say, fill a, for my schematic, topology connection branch with nodes determined by the first incidence matrix. But we need to know branch resistance, capacitance, inductance, and so on. They are put in the resistance matrix. It's a matrix with a structure branch and branch. It's a square matrix. At a main diagonal. Wait 1 second. I need.
It's always a square?
Yeah, it's always square.
Branch versus branch.
Branch and branch. Main diagonal is filled with branch, let's say values.
Okay, so first branch resistance,
Yeah,
second branch resistance.
1 second I will write. Second and so on, and branch resistance. For active resistance we write, for the coils we write J omega L. For capacitors, 1. It all goes to the main, let's say main diagonal. So elements with index G3 are branch own resistance. If we have mutual inductance, let's say this will be, and this will be, I don't know, let's say K. If we have two branches coupled with mutual inductance, we write symmetrical Kn omega n. So matrix other elements are filled with mutual inductance.
Can't we just add the two inductance? That won't work? No, it won't work.
No, we don't have them here. In case we have transformers, something like this, and we want to represent mutual inductance, we write them in the resistance matrix as non-diagonal elements. They will be symmetric. So if between branch L and K is a mutual coupling, they are connected with common magnetic flux. We need to write symmetrical as a J omega and
Then-
mutual inductance.
But then what if it's from two different branches?
Yeah.
One inductor will be in one branch, the other inductor is in another.
So wait 1 second. Each branch will have two inductance. Own inductance and mutual. Own inductance go to the main diagonal and mutual as mutual element.
Oh, yeah. Not circuits, basics.
We found them right in there.
Yeah.
And now, one moment. See, I have K here. For each Fourier row element, frequency will be K omega. That's why for coil we write K omega A. For capacitors, 1 K omega A. Number of harmonics.
C, omega C.
Capacitance. Yes. It should be capacitance. It should be capacitance. Mutual inductance. J K omega.
Is this for the matrix or is this for something else?
It's how we fill this matrix. We will have 50 matrix.
Yes, exactly. So all
Yeah, but we don't need to store them in memory. Since we calculate one regime in time, we will recalculate this matrix. But yes, for each AC component, we create its own resistance, or better, impedance matrix. Take a look. Number of harmonic
50, yes.
from 1 to 50. Count 1, 2, 3. Machine counts 1, 2, 3, 4. For each frequency is recalculated and matrix is recreated. The first branch was 222 ohms. The second branch 8 millihenries. The third branch 94.7 microfarads. You see, 94.7.
Capacitance, right? Okay.
Yeah, it's a capacitance. 1 divided by 79.4 ohms, 6.8 millihenries. Matrix is recalculated for each harmonic. This one. Next one.
Professor, why isn't there a K inside the equation? Because it's 1, 2, 3, right?
Yeah, because first harmonic,
Second
50 hertz. Second,
100?
100. Third, 150. That's why frequency changes.
Ah, okay, frequency. Okay.
This one counts the number of harmonic, and for each harmonic, frequency changes, and resistance matrix recalculated. The same with AMF. We need to set an AMF vector. It's a vector by branch. If EMF is, let's say, coherent with the branch direction, we should write it with the plus sign. If it goes in opposite direction, we should write it with the minus sign. In our case, this vector fills with elements from Fourier decomposition. Okay.
So this is a single line matrix.
We have only one source in our case.
Branch, only branch.
Only one branch. We replaced the rectifier with the elements from Fourier. And here it is, one EMF which takes value of CK. Here we have minus. 1 second. Yeah, it's a complex. Complex function grows complex number from a real part, cosine coefficient, and imaginary part, sine coefficient. Only one, this minus sign, because Fourier rule started from cosine. To be in let's say in harmony with our basics of electrotechnics, I need to implement this minus. Now, the next step. This one is very simple. I need inverse of resistance matrix, but since I don't have any mutual inductance in my schematic, I can use a very simple way, just invert main diagonal. And here comes the most needed part from electrotechnics. I will solve a nodal potential or nodal voltage equation system. 50 times I need to do it for each harmonic.
Professor, that swaps the matrix upside down, right? The Z1 II, it's
No,
still upside down.
inverts.
Okay, but you just say
I need this one, inverter.
inverse.
Inverse. What I need to do? I need to solve equation system. It's a system of nodal equation. Current sources, I don't have them. I have introduced only EMFs. For some special case, if I have source as a current, my rectifier is source as a voltage. If I need to do something when original source is a current, this one will become, but it's all, in my case, this one at k omega multiple, this one multiple from Fourier law at k omega. If I have source, I need to deal with current, with, I don't know, with driver, something like this. Here will appear elements at k omega. In this task, I don't have current sources, so I can ignore. This one is current source vector, and this one is EMF vector. I use, at necessity. When I need to represent currents, okay, I fill current source. When I have EMF, no problem, I have a place for EMF. This one, nodal conductance matrix.
Okay, Professor, but if we have current, then EMF also will be there?
As needed. They can be both, no problem.
So it's,
As needed. We can have both.
but you can also only have current?
If only current, this one disappears. If only EMF, this disappears. Both, no problem.
And what is M?
What?
What is M?
No, first incidence matrix,
Oh.
branch nodes
Okay,
connection.
okay.
In general, it's a linear system of linear equation equals nodal conductance matrix, node voltages, and three elements, currents and EMFs.
Professor, what is that called again? YU? Nodal
Voltages,
nodal voltages or current?
voltage. We solve with the aim to get node voltages. What's the difference? I think you heard as nodal potentials. In something like for graphene, the difference is what I can add base voltage not zero. In the node voltages technique differs from node potentials. What I can use, for example, for calculus of power networks, with non-zero base voltage. No problem, just add 1 to number of nodes for E starting from, but it's not our case. Let's go a bit further. What we have here. I have calculated nodal admittance matrix. This is nodal admittance matrix. Three members, and at this row I call built-in Gauss or sequential exclusion method solution. Gauss solution for the system of linear iteration. I can use Zeidel or something like this. I'm lazy, so I used built-in Gauss. And final branch currents with the help of Ohm law in matrix form.
With alternative RMS values.
Not important. The ideal square root of 2.
Professor, is this uploaded in Nodal, this file?
I will share it, no problem. What's the idea of file without understanding what's inside? Now, one more step remained. DC component.
That's constant.
Wait 1 second. I need all voltages and all currents of DC regime when DC source is applied instead of my rectifier. And here is problem. What kind of problem? What will become capacitor in the DC regime? Resistance of capacitor will be infinite.
Yes.
So this branch should disappear from the schematics. Yes?
Okay, yes.
Yeah. What with the ideal coil? Resistance of ideal coil is 0. So ideal coil should disappear and become a bus, let's say, a direct connection. Internal resistance of, if coil has a counted active resistance, it will remain, but inductive part should disappear. This means what I need, what? Separate schematics for DC regime. With separate nodal matrix, it's all separate. Again, I'm lazy. What I'm done? I'm calculating DC regime as an AC regime at a frequency 1 milliradians per second. It's a very slow AC regime. Some 20 milliradians don't change anything.
So it's all zeros?
Near zeros. I'm calculating DC regime as AC at a very low frequency and with DC component as an EMF. That's the way how it's a fast and dirty way to get DC regime. To calculate it as AC at a very low frequency. It's brutality and pornography, but I did it. So the same code. What have I done? If you see, See this row. What I'm doing? All elements in a corresponding column should be filled with solution results. I got matrix. It has 50 columns, and how many nodes I have? 5, and 5 rows. So each column corresponds to 1 omega, double omega, triple omega, and so on. And numbers, row numbers are corresponding to the node numbers. So I have now matrix 5 by 50 filled with voltages. Each column corresponds to its partial regime. Column 51, see, will be filled with DC regime. Now I have 51 column describing my schematic voltages at all frequencies including DC. Now I would like to get voltages. Fourier synthesis. Take a look. Time step. This first one. C0 divided by 2. DC component. Next. Since from this basic electrotechnic solution I got complexes, I need to go back to Fourier coefficients. So a real part will be cosine coefficient, and imaginary part will become sine coefficient. What it should be? And with the help of plot, I can get my voltages as charts. Let's see. Okay, execute till the current. Yeah. Wait 1 second, they are coming. Here they are, my voltages.
That's omega 1, omega 2?
No, it's a first node, second node, third node, fourth node, and fifth node. Voltage by nodes. For the, just for fun. Just for fun. Hey, come on. I'll switch to simple rectifier. What I'm doing. Oh, here they are, bit chaotic. Something goes wrong here. 1 second. Do I have? execute with echo till current. Yes. Note they are correct. Why I can get, I need graphic window number 2. Oh yeah, I correct for recording. Voltages in case of ordinary rectifier. Node voltages. Can I switch back to not needed. Okay, and go on. Till, if I want to execute till current, I need to stand here. You can see much better three-phase rectifier. The real produce less distortions. And just remaining, we have voltages and there are currents. I need currents. This one is no longer.
Generally, we need both, right, Professor?
We can get all of them. No problem. I already have all 51 currents. I just need to apply Fourier synthesis. We'll get everything. Voltages. Currents.
How many currents are there?
10 I see.
Okay, it depends on the amount of nodes, right?
Of course,
Yeah, 5
depends on schematics. Wait 1 second, why can I get? This one is window number 3. Yeah. For recording, I get currents. Here they are, voltages and currents. Just for example, I can switch back to simple rectifier. Okay. Okay, execute. Oh no, they are overlapping. It was mistake. It was mistake. Then voltages, and here they appear currents. More distortion. It can be expected.
This is one phase, right? Two phase, one phase.
This one is one phase.
One phase. The other one is four phase.
Three.
Three phase.
Mhm. Four phase. 1, 2, 3, 4. Like Star of Chaos. Yeah, for recording I put currents on the screen. So it's how it works. So, general idea. Create table of signal, apply discrete time Fourier transform, solve AC regimes, get an array of partial regimes. When array is filled at couples one step, perform a solution of DC regime, always, in my case, using nodal voltage method with the help of nodal admittance matrix, and perform a synthesis to get results in time. All this took 131 row.
Piece of cake, yeah.
No, nothing special. Come on, it's written in 20 minutes.
Really? 20 minutes?
Real.
Like you typed everything?
Yeah. The most work was to create a matrix. I needed to draw a schematic on a paper.
Professor, if you could give us a schematic, maybe we can give it a try. If you give us a schematic, then we can try and do the same thing.
Schematic, we can try.
And the values of capacitors, inductors,
Yeah.
resistors.
Easy.
That's all we need. Schematic.
Easy. Easy. What easy? Only one. 1 second. What do we have? What do we have at L-Unix system? What we got here? Let me in. Machine. task here. Okay, good news, I have such task. Bad news, it's in Latvian. I need to fast.
Only the schematic is enough. And we just need to do the same thing, right?
Yeah, the same thing. It's schematics without numbers, so you can choose numbers at your will.
No numbers? Why?
Because you can set them as you wish. It is not. See, the element numbers are not important. Value, we need elements values, but numbers itself not important. They're only important how they are put in the matrix. Okay, you can use another approach. You can not create a matrix once and for all. You can use a database of elements and combine matrix on the fly ad hoc. In such case, number will be important. But if you use hard-coded matrix, it is not important which numbers are written on schematics. The only important is position in the matrix. Okay, now I will publish it. I need my another computer.
No worries.
Wait 1 second. Wait 1 second. Maybe I'm dumb. Wait 1 second. Maybe I'm dumb. I see Latvian. I see trace. I see Latvian test. That sucks. That sucks because I don't see translation. Okay, you know what? I'll fix it. We have what we have today.
We have
Another.
30.
I'll create them. No problem. Only place my mouse.
We have something after that.
No.
Have something
I will write them. One moment. I will publish this code first.
Professor, can we take a 10 or 15 minute break?
No problem.
We'll be back. And if we can finish by like 1:30 because I have to be somewhere else.
Okay, we will. I'll end stream now. I will put this code and stream reference to the e-learning system, and I will fix tasks. I have